Alright, in this video we're going to translate some sentences into quantificational logic, and then we're going to negate some quantificational logic statements and reduce them as far as we can. Okay, so first question, we're going to translate these. So our first question is, every student is majoring in math or computer science. So I'm not going to define anything explicitly, but I just want to show you the process here. So first we have every student. So we have for all x, if x is a student, so we're going to call that s of x, then that student is going to major in math or major in computer science. So this means that if x is a student, then x majors in math or x majors in computer science. So here we have it. For all x, s of x, arrow, mx or cx. For all x, if x is a student, then x is a math major or x is a computer science major. Okay. Second question, for all real x and y, if x is greater than y if x squared is greater than y squared. So for all real x and y, so this is for all x in the real numbers, for all y in the real numbers, x is greater than y if x squared is greater than y squared. So here we have if x squared is greater than y squared, then x is greater than y. So that's what that one looks like. For all x in the real numbers and all y in the real numbers, if x squared is greater than y squared, then x is greater than y. I changed the order of the if there, just to mess with you a little bit. Okay, the last one, for all epsilon greater than 0, there is a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon when x minus a is less than delta. You might see this in a calculus course, so you might be familiar with this. Let's change that into quantificational logic. Okay, for all epsilon greater than 0, so for all epsilon greater than 0, there exists a delta greater than 0. So there exists a delta greater than 0 such that, so we can start our bracket here. The absolute value of f of x minus L is less than e when x minus a is less than delta. So this when is just like the if. So when is if. So that means that x minus a is less than delta, then we get that f of x minus L is less than epsilon. So our translation, for all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Okay, so those are three translations. I almost guarantee on any midterm, you're going to get this question. You'll probably get this exact question, and you might be asked to negate it. So let's do some practice with negations. Negate exists in x, p of x, and q of x. So I didn't put the brackets around the p of x and q of x. Stylistic choice, I guess. So, negate it. So we start. Negate, there exists in x such that px and qx. So, first thing we do is we put that negation next to the quantifier. So first step, we want not exists in x, px and qx. So when we have an encounter like this, not ex or not exists x px, we get for all x, not px and qx. So this is how negation works. The negation comes in, it flips the exists to an all, and then it negates everything after it. So now we have for all x, and of course we just use De Morgan's law here, and we get not p of x or q of x. And there you have it. If there does not exist an x such that px and qx, that's the same thing that's saying, oh, oops, there should be a negation here. That's the same thing as saying for all x, it's either not p of x or not q of x. Does that make sense, right? I want to say there is some number that is odd or even. Okay, so now I'm saying, look, there's no number, that there is not a single number that is odd and even. And that's like saying, well, look, all numbers are either not odd or not even. So we have that English translation there that may assist you with this. Okay, here's another one. All x, px, arrow, qx. So let's negate this. So we have not all x. Again, of course, the screen is being ridiculous here. Not all x, px, arrow, qx. So the first thing, the negation comes in. It flips this all of x to an exists in x, and then it negates the rest. So we have not px, arrow, qx. Okay, so we should use the definition of the conditional here to make this easier to work with. So we have not p of x or q of x. And then we just use De Morgan's law to come in there. So we have not p of x and not q of x. And of course, the double negation just gets rid of the two negations in front of p. So not all x, px, arrow, qx is the same thing as saying there exists an x such that p of x and not q of x. So for instance, for all integers, so for all x, if x is an integer, then 2x is even. So if x is an integer, then 2x is even. Yeah, that statement. So if I want to say for not all of x, if x is an integer, then 2x is even, that's the same thing as saying there is some x such that x is an integer, but 2x is not even. So again, English translation to help you understand the relation between these two here. So if you have any other questions, please leave them in the comments below, and I will answer them as quickly as I can.